Hello everybody, welcome to this tutorial. My name is Dr. Garma Abdisa. In this tutorial we are going to talk about properties of vectors. Parallel or antiparallel vectors. Two non-zero vectors A and B are parallel or antiparallel if A cross B is equal to 0. Let us illustrate if this relationship holds. Let us begin with considering a vector B and another vector, vector A, and the angle between these two vectors is theta. Let us reconstruct them such that they would form a parallelogram. This is the altitude of the parallelogram, which is the magnitude of vector B times sine of the angle between the two. If vector A and the vector B are represented by direct line segments, such as shown in this diagram, with the same initial point, then they determine a parallelogram with base magnitude of vector A and altitude magnitude of vector B times sine of theta, which is the angle between the two vectors, and the area is given by the magnitude of the cross product of the two vectors, A cross B, which is magnitude of A times magnitude of B times sine of theta. We could write this relationship directly because the area of the parallelogram is base times height. The base is magnitude of vector A, and the height is magnitude of vector B times sine of the angle between the two, which is simply the cross product of the two vectors. If this is so, if these two vectors are parallel, or if they are anti-parallel, means that no area will be left between the two vectors, so the area is 0. This gives us an option to judge if any two vectors could be parallel or anti-parallel by simply using the cross product. If the cross product turns out to be 0, it means that these two vectors are either parallel or anti-parallel. Coplanar vectors. Three non-zero vectors A, B, and C are coplanar if A dot with B cross C is equal to 0. Coplanar means all of these three vectors A, B, and C lying on the same plane or sharing the same common plane. As an illustration, let us consider these two vectors, that vector B and another vector which is called vector A, and still another vector, vector C, so that they would form an angle theta with the y-axis. And let us reconstruct them so that they would form this volume. If theta is the angle between A and B cross C, then the height h of the parallelogram is h is equal to magnitude of A times cosine of theta. So this height is simply magnitude of this vector A projected onto this axis, which is this part, that is h is equal to magnitude of A times cosine of theta. We must use cosine of theta in absolute value instead of just cosine of theta in this way, in case theta is greater than pi over 2. Therefore, the volume of the parallelly piped is V is equal to A times h, that is the base area times height, and the base area is simply area of the parallelogram as we saw it earlier, which is equal to simply B cross C, because the base is made between two vectors, that is vector B and vector C. So area of this base parallelogram is simply B cross C times the height is A magnitude of vector A times cosine of theta, that is this height h. When we rewrite this vector into a vector form, we can write that as a magnitude of A dot B cross C. If the three vectors are coplanar, or if all of them are on the same plane, it means that their volume must be 0. Because if all of them are on the same plane means no volume will be left in between those three vectors. Perpendicular vectors. Two non-zero vectors A and B are perpendicular to each other if A dot B is equal to 0. To illustrate this, let us consider this vector A and another vector, vector B, having an angle theta in between them. So we can write A dot B is equal to magnitude of A times magnitude of B times the cosine of theta, and this is simply the basic definition of dot product of any two given vectors. So from this relationship, directly theta is a cosine inverse of A dot B divided by the product of the magnitude of the two vectors. And if A dot B is known to be 0 already, then theta is a cosine inverse of 0 divided by the product of the magnitude of the two vectors, which turns out to be the cos inverse of 0, which is 90 degrees. So if we have 90 degrees in between the two vectors, means these two vectors must be perpendicular. Properties of the dot product. The dot product has the property that, number one, A dot with A, that is any given vector dotted with itself, is equal to the magnitude of that given vector squared. A dot with B is equal to B dot with A. The change of position in the dot product doesn't matter. A dot with B plus C is equal to A dot B plus A dot C. The zero vector, this is called the zero vector, dot with any given vector A is equal to 0. Let us solve some problems. Show that A dot with B plus C is equal to A dot B plus A dot C. We can solve this problem by rewriting A in full Cartesian coordinate as AXI plus AYJ and AZK, and the same applies for B and C. So A dot in parentheses B plus C can be written as AXI plus AYJ plus AZK dotted with the sum of the other remaining two terms that are B plus C, BXI plus CX in I, BY and CY both in J, BZ and CZ both in K. So by directly multiplying them component-wise with each other, we get AX into BX plus CX, AY into BY plus CY, AZ into BZ plus CZ. This is by directly applying the basic definition for the dot product of any two vectors. And finally, we can rewrite this final expression as AX BX plus AY BY plus AZ BZ plus AX CX plus AY CY plus AZ CZ. And by collecting these terms, we can rewrite as A dot B plus A dot C. Find the angle between the vectors A is equal to 2i plus 2j minus k and B is equal to 5i minus 3j plus 2k. So A dot B can be written as the dot product between the two. We simply multiply I term with another I term, the j's from both sides to be multiplied with each other. The same applies for k, and finally we get A dot B to be equal to 2. Magnitude of A is the square of the sum of the components squared, which is equal to 3, and the magnitude of vector B is equal to, it is components squared taken under the square root, again equal to root of 38. So theta is equal to the cos inverse of A dot B divided by the product of the magnitude of each vector, which is the cos inverse of 2 over 3 root 38, which gives us 84 degrees. The second example, if A is equal to 4i plus 2j minus k and B is equal to 2i minus 6j minus 3k, then calculate a vector that is perpendicular to both A and B. A vector which is perpendicular to both A and B must be another vector, vector C, which is the cross product of the two vectors. Because by definition, if we are given two vectors A and B, then their cross product, namely A cross B, is perpendicular to both A and B. So we simply find a vector C, which is the cross product of the two vectors, and for simplicity we write it in the matrix form, and then we get C is equal to negative 12i plus 10j minus 28k. If you are not sure how this matrix multiplication for the cross product of any two given vectors, you can watch another video tutorial which focuses on the cross product of vectors. Let us check if this final answer, that is vector C, which is equal to minus 12i plus 10j minus 28k, is really perpendicular to both of these two vectors, A and B. So according to our requirement for perpendicularity of any two vectors, if C is really perpendicular to A, C dot A must be 0, and C dot with B is also equal to 0 if C is perpendicular to B as well. So C dot with A is clearly 0 if you multiply, and again theta is equal to the cos inverse of 0, which is equal to 90 degrees. So in fact C and A are perpendicular. C dot with B, with the same procedure, if you make a dot product between C and B, you will again get 0. So the consequence of this is that theta is the cos inverse of 0, which is once again 90 degrees. So again B and C are perpendicular. So our answer is right. The third example shows that the vectors A is equal to I plus 4j minus 7k, and B is equal to 2I minus j plus 4k, and C is equal to minus 9j plus 18k are coplanar vectors. If they are coplanar, then A dot with B cross C must be equal to 0. B cross C is given by this expression. If you are not sure with how this could be obtained, you can watch another video tutorial on this specific topic, on the cross product of vectors. And A dot with B cross C is therefore AX multiplied by the x component of this B cross C, which is the term in the parenthesis here, also for J and K, and then you can directly write this relationship. Or in matrix form, you can write A dot with B cross C as AX AY AZ, BX BY BZ, CX CY CZ. And you can rewrite that, you can reduce that as by cancelling the columns and the rows, AX into BY CY BZ CZ minus AY into BX CX BY CZ plus AZ into BX CX BY CY. This kind of matrix simplification is really very important to tackle this kind of problems. So as a solution to our particular problem, A dot with B cross C can be obtained using this simplified form of a matrix. Then A dot with B cross C, upon manipulating this matrix with little algebra, you finally get A dot with B cross C to be equal to 0, which is in support with the idea that these three vectors A, B, and C are coplanar. Means all of them lie on the same plane. In other words, the volume between the three vectors A, B, and C is 0. No volume is created because all of them are on the same plane.